All right, class, chapter 7 is going to be on linear regression. So we look at this scatter plot from Burger King that is grams of fat versus grams of protein. We see from the previous chapter that there is a strong positive correlation, and it is linear, as in you can see, you can almost draw a line right through there to cut through the middle of it, right, like that. And that's the key to this chapter, is that you actually can draw a line that cuts through the middle of these, and it's called the regression line, and we're going to get to that. So the correlation here is 0.83 on this one. And so that is a strong, positive, and linear association between protein and fat. And you would think there would be. A burger like that, if it has a lot of protein, it'll have a lot of fat in it, because, you know, the size of the beef patty. And in this chapter, we'll say more about this linear relationship between the two variables. It's called a linear model. And the linear model is just an equation of a straight line through the data. So it's just a straight line going through the data like we talked about. And the points don't all line up, but a straight line can summarize kind of the middle of them. They won't be exactly in the middle of all of them. But the linear model can help us understand how those values are associated and give us a way to predict other values that might happen. So the linear model is not going to be perfect, regardless of the line that's drawn. And they say, and like we said, all models are wrong, but some are useful. So a lot of these, especially if you have a really good correlation, it can be very useful in predicting future data. And a prediction is going to be the little Y with the hat above it like that is the model you'll see for the prediction. So the difference between the observed value and the predicted value is going to be called a residual. So we're going to use the formula we come up with, that line, to predict values, and the actual values observed minus the predicted is going to give us what's called a residual. It's going to tell us how accurate our line is, and how accurate it would be for predicting future points. And the good thing about this is if you added up all the residuals of a graph, you'd end up getting 0. So for the correct drawing of that line, when you add up all the residuals, they end up being 0, because there's about equal amount on each side, right? So let's look at a picture like this of the residuals right here on this line. You know, some of them go down this way, and they're a certain distance away from the red line is our regression line, and some of them are below it, some of them are above it, like that. And if you drew the line correctly, and you're going to have a software program, either like Staplet, or you're going to have your TI-inspired calculator, and it's going to know the equation to find this line. You won't have to actually calculate the line. You'll have a calculator do it for you. And what it is it's a line that, if you added up all the residuals, they would be equal to 0. So it's like the same distance apart from the middle of the line. So a negative residual means that you have an overestimate. Because look at the equation y minus y hat. And that is predicted. Actual minus predicted. And that is actual. Because the actual is the actual dot itself, the y, minus the predicted. So a negative residual is an overestimate, because you'll end up with a negative number, right? If you look at this right here, that means you overestimated. The prediction is higher than the actual, so you end up with a negative number, right? Like if the actual was 7 and the predicted was 10, you would end up with negative 3. So that's how I'd be an overestimate. However, if you had an underestimate, that means the actual is actually higher. Like the actual is 12, and the predicted is 10, you would end up with 2. Like one of these above it, like say this is 12, and the line hits at 10 right here. That would be 2. So that's how that works. That's what this line does, is it splits it right in the middle, where if you added up all these distance ones on the bottom and you added up all these distance ones on the top, you'd end up with 0. All right, the next concept is called the least squares regression line, and this is the common name for this line. So I would write that down. The least squares regression line is the common name for this line that is made that goes through the middle of the data. And some residuals are positive, others are negative, but they cancel each other out, right? So we can't assess how well the line fits by adding up all the residuals because the sum would be 0 every time. So that doesn't really tell us a whole lot. So what you do is you square those residual numbers, like these numbers you get right here, you square them. And this will give you the least squares regression line. And so the line of best fit is the line that minimizes the sum of the squared residuals. And it's called the least squared regression line. And that's how they calculate this. So what they do is you're that far away. See, say it's like 3 or something. It would be a little box of 3 because 3 squared, right? 3 times 3 is 9. And it's literally would end up just being a bunch of squares, right? Like this one, a little square. You go to there and you make a square out of it. And the least squares regression line is the line that you can make that would make the smallest area of squares that would end up being on the graph. Would be called the least squares regression line. You're not gonna have to calculate that. The calculator or Staplet will do that for you. But what it does is it minimizes the residuals and makes those squares as small as possible. So here's another example of the figure shows the scatter plot of z-scores for fat and protein. If the burger has an average protein content, it should have an average fat content too. So moving one standard deviation away from x moves us r standard deviations away from the mean and y. So this ties into the correlation, the r value. You're not going to need to know this like in super detail, but this just wants you to see that that correlation is tied to this. And it's tied with how many standard deviations away you are. Because remember, the r equation had the z-scores involved. So it's just a good example that the R scores and the Z scores are all tied into this stuff. It's kind of going to be going on in the background when you're going to calculate this in Staplet, but there will be a relationship going on in the background. So put generally, moving any number of standard deviations away from the mean in X moves us R times that number of standard deviations away from the mean in Y. That's that correlation value and how it relates to this line. So how big can the predicted values get? The R cannot be bigger than 1 in absolute value, so the predicted Y tends to be closer to its mean than its corresponding X was. So the property of the linear model is called the regression to the mean. So this is called a regression line, what we're doing here. All right, so the next thing is one of the really important things in these notes is this regression equation. So your normal equation for a line is y equals mx plus b. You should remember this from algebra, where m is your slope and b is your y-intercept. Well, they write it a little different in statistics. In statistics, they'll use y is equal to b naught plus b1 times x, where b naught is the y-intercept. So they put the y-intercept in front, and they put the slope second. And the most common way... So this is in stats. This is how you see it. And this is also in a TI Inspire. You'll see it written like this, so you need to know this as well. A plus BX. They'll call B naught A and B1 B. They'll call it A plus BX. So these are 3 different ways you'll see it, but it means the same thing on all 3. Where the one with the x on it is going to have the slope. You know, the number in front of the x is always the slope. So this is the slope, this is the slope. And the number by itself, like a constant, is the y-intercept. Oops, that should be pointing to that right there. That's the y-intercept. So you need to know the general form of the functions. Now, B1 is our slope. Remember that? And B1 is going to be equal to, this is the key equation you need. This kind of messed up this slide, but this is on your outline as well. And the really key one that we're going to use in class is that B1 is equal to R times SY over SX. Right there. It's the correlation times the standard deviation of Y over the standard deviation of X. And that is your B1. That's the one I would circle on your formula sheet right now. The B1 is equal to that. And it means that for every X unit increase, every time X increases, there is a predicted jump in Y by this amount right here, by the slope. Remember, slope is like rate of change. It goes up by this much for every 1 unit of the X. Y goes up this much. So this is how much Y goes up as compared to X, and it's like a slope, right? Remember rise over run? So that's how that works. And then the B naught is the y-intercept of the line. Remember we have, if you have the formula, y equals B naught plus, minus B1x. See, that's the mx minus b. Oops, my bad, plus. Yeah. Yeah, and all they did right there was just solve for B naught. They solved for the y-intercept. And basically, this is the y-intercept when x is equal to 0. Because remember, a y-intercept is when x is 0. Y is going to be equal to B naught. So this is basically just algebra again, just written a slightly different way. It's not as complicated as it looks, especially when we get some problems. You'll see how it works. So remember the correlation coefficient, that R shows the relationship, it'll show like a strong positive relationship between the two variables. Since R cannot be either positive or negative, they use R squared a lot in statistics, and they call it the coefficient of determination. It's basically the square of the correlation. And R percent of the variation of Y description can be explained by the linear relationship between the two. So if you have a really high R, like a really high R squared, like say R squared was 0.95, that's super high. That means they have a 95% relationship to each other. 95% of the variation can be described by their relationship. So this is basically how accurate your line is going to be too. It's just how strongly tied these two variables are and how much they have to do with each other. Like a perfect one would be 1.0, which is 100%, which means they're directly correlated. If an R squared ever ended up being 1, which would be super rare. All right, so the next is the example, but we're going to continue with the slides. We'll do the examples on another video.